Now that we've finished explaining the basics of special relativity, we can tackle the core subject for today, which is relativistic electrodynamics. And the first thing we're going to do is try to see how our Lorentz transformations play when we've got some electromagnetic fields present. So for that, we're going to consider some very, very simple situations. Let's consider the following thing. So I've got a setup in which there's a wire, thick wire like this, and this wire carries a net current, and this net current is composed of two pieces. First of all, there's a line charge density lambda moving at a certain velocity v towards, in these coordinates, the right. Okay, nice little arrow here. But also present in the wire is another piece of current which has a line density minus lambda, and which moves at velocity towards the left, if you want, so velocity minus v. That means that, so here I'm in the lab frame of reference, okay? It means that the current in my wire in the lab frame of reference is equal to 2 lambda v, right? And then on top of that, what we're going to consider is a little charge q moving at a certain velocity u here in the lab frame. And we're going to take that the u is going to be smaller than v just for arguments purposes. Okay, so in the lab, there are no electrical forces. No electrical force between the wire and the charge, because the wire overall in the lab is charge neutral. So the only thing that you have is a current. Therefore, you've got some magnetic interaction, of course, but the electric field vanishes. Okay, so now if we look at the situation from the particle's point of view, I'll just say it's Q. Q is our particle. Then the things are different, of course, because in the frame of reference of the moving particle, the currents don't move at the same velocity. In fact, the current going to the right and the current going to the left will have a correction coming from the law of addition of velocities, but this correction is going to depend on the direction because of the fact that u is different than 0. So the current velocities in the frame of the moving particle, we're going to label them v plus or minus, plus for the plus current and minus for the minus current. Then by the law of addition of velocities, it becomes like this, 1 minus or plus uv over c squared. Okay, so now we have that the velocity of the negative charges relative to the moving particle here. So in the frame of this particle here, the negative charges move faster to the left than the positive charges move to the right. Therefore, the Lorentz contraction factor is going to be different for the two. And these two line charges are therefore going to add up to something that has a non-zero net charge. Okay, so let's just do the Lorentz corrected line charge densities. So what would those be? Well, I would have a lambda plus or minus is equal to plus or minus, just coming from the original sign of the charges that I had. But then I have a correction factor gamma plus or minus times lambda 0, where lambda 0 here It's the line charge density in the frame of the line charges, right? So it would be the line density at rest if the charges weren't moving. Okay, now how do you compute this thing? So what can we say? Well, the gamma plus or minus, we know how to compute that because it's just our habitual factor. 1 minus v plus or minus squared over c squared, right? So what we would further write is that there's a relation between lambda and lambda 0. So the lambda, that's equal to gamma times the lambda 0, where this gamma here is just the velocity of these charges here, okay, in the lab frame. So gamma is just 1 minus v squared over c squared, square root. Okay, so far so good. Now we can rewrite this thing in a simplified manner. So if I look at gamma plus or minus, I will now want to substitute the form of the velocities here into this form and see what I get. So what is gamma plus or minus? 1 over 1 minus then v plus or minus squared. So I've got this, and I've got a factor of c squared. Yeah, so it's all a bit of a mess, right? But let's just try it out. So v minus or v minus u. Sorry, here I should do minus or plus u. V minus or plus u squared divided by this thing here. So 1 minus or plus uv over c squared, and then of course there's a 1 over c squared here, right, coming from this one here, and all this in the square root. Okay, so let me just like remultiply this denominator here. I'm going to scale everything with the light velocity. So what does that tell me? C squared minus or plus u divided by the square root now of, again, this c squared minus or plus uv. This thing squared minus c squared times v minus or plus u squared. Okay, and this in a square root. Right, so I can just simplify the things here. You see, I've got a c to the 4, which stays. I've got the minus or plus 2 c squared uv, and then you see this one would disappear against this this one, the cross term here, and then I would be left with a c squared v squared, c squared u squared. Okay. So I can just recognize the form that in the numerator I got minus or plus u, and then in the denominator, just collecting terms, I would have you know, the v appears like there, and I would be able to factorize c squared minus v squared times c squared minus u squared, and that in a square root. Okay, and I can just recognize my factor. So I've got a factor of gamma here. Okay, and then I have a leftover. So the gamma that I have here picks up this one here, and then I divide by, sorry, I'm forgetting a v here, yeah, uv in this uv, that just came from this term here, Then besides the gamma, I'm left then dividing by the c square overall, left with the 1 minus or plus uv over c squared divided by the 1 minus u squared over c squared in the square root. Okay, so that's the result for my Lorentz contraction factors for the two parts of the moving current. Now the resultant line charge density in the frame of the moving charge, I'll call it lambda. Maybe I should call this like the test charge. Maybe I'll call it. Maybe that's confusing. I'll just call it test. Yeah, so that's in the test frame. So what is this? Well, it's really just the two parts, lambda plus plus lambda minus, that were given here. And now I can substitute the form of the factor that I have here. And I see that I just get simple simplification here, where I just pick up this part of the term here, because this thing becomes just lambda 0 times this gamma plus minus gamma minus, which is equal to just minus 2 times this lambda uv over c squared times 1 minus u squared over c squared. Okay, so the gamma that we had here combines with the lambda 0 that we have to just produce the factor of lambda that we have here. So this is quite interesting because in this frame, the wire is charged. Okay, so Lorentz contraction has contracted the negative charges more than the positive charges. Therefore, overall, you pick up a negative line charge onto that that system. So what does that mean? There's then an electric field, yeah, and the electric field would be that of just a simple wire, like we know. Okay, so the electric field is different than 0, and what it would be, the electric field would be, as usual, you remember how that is, so there would be just the following field as for the wire, like we've done in electrostatics at the very beginning, 2 pi epsilon 0. There would be a coordinate s in cylindrical coordinates, just the radial distance away from the wire, and of course the field would be pointing out in the direction of the radial direction in the cylindrical coordinates. Okay, so E, if you want, is s hat like this. Okay, so the force is non-zero. The force in the test frame, yeah, maybe I should say test in the test frame, it's just Q times this electrical field in the test frame, and that is just Q times this thing. Okay, so times this linear charge density put in the formula for the field. So just collecting terms, I've got the minus lambda times V times U times Q, okay? Then divided by pi epsilon 0, we've got a c squared, and then I've got 1 over s, and I've got the factor here, just 1 over 1 minus u squared over c squared, square root. Okay. So, so that's interesting because it now means that we've got a force acting on our particle in the an electrical force in the frame of the moving particle. But you know, I can just rewrite this thing here by recognizing a couple of things. So just use that 1 over c squared is equal to epsilon 0 mu 0. You see, I've already got the epsilon 0 c squared. So this thing here is just 1 over mu 0. So I just have a mu 0 on top. And the other thing I can use is the fact that I had the current, which was 2 lambda times v, right? That's where we started from. Just didn't like that v. So 2 lambda times v. So this thing just becomes equal to q times u, so minus q times u, and now I've got the mu 0 I over 2 pi s. Okay, and that you should really recognize as the you know, QV cross B, right? So where B is generated by a line wire. So this is like the Lorentz force. For charge Q moving around the wire carrying current I, like we've seen in electrostatics. Okay, so this is the kind of magic that you can operate with very simple look at the effects of Lorentz contractions on your system. And this is really quite interesting because in one frame, I emphasize, there was no electrical force. But then in the other frame, when some moving observer looks at the same situation, there is an electrical force. But fortunately, the two things completely correspond to each other because you see in that case, so how does it work in total? So in the original frame, I've got a magnetic force coming from the wire that acts on this, this charge here, moving at a velocity v. But this charge only cares about the electrical field coming out of, it cares about the electric field and the magnetic field. So the electric field is 0 in that frame because the currents, the charges are essentially adding up to 0. The current's non-zero, so by Biot-Savart there's a magnetic field which gives through the Lorentz force a force on this one. In the frame of the moving particle, however, the Lorentz force is exclusively due to the electrical field because the velocity is 0, there's no magnetic part to it. But then, because of the Lorentz contraction in that frame, the electrical force is not 0 and precisely corresponds to the original magnetic force in the original frame. Okay, so that's how it all adds